Lecture 1-3, Scientific Measurement and Dimensional Analysis. Measurements gives us three types of information. First of all, the magnitude or the size of the measurement is given as a number. Second, a standard for comparison of the measurement, that is a unit or dimension such as meters, feet, or milliliters. And an indication of the uncertainty of the measurement, which can be just the last digit, is designated as a measurement of uncertainty, or you can see things such as plus or minus after the number, or sometimes in parentheses the degree of uncertainty is given in a more precise manner with the parentheses. Measurements can either be quantitative or qualitative. Quantitative is used expressing numbers as the measure. For example, test scores, length, volume, and most measurements that we do in chemistry are quantitative in nature. The other is qualitative, which is expressed using properties such as good, excellent, and poor. Sometimes qualitative measurements are given star ratings, so we get a feeling for a number that is actually an expression of an opinion as opposed to an actual measure of a quantity. Here are the 7 basic international system units. Length is measured in the meter. Mass is measured in the kilogram. Time is measured in the second. Temperature measured in Kelvin. The amount of substance is measured in a mole. Electric current is measured by the ampere, and luminous intensity by the candela. All other measurements that we see in the SI system are derivatives of this. Sometimes they have special names associated with them. This slide is a little bit outdated, and that is in the mass portion down at the bottom, but measurements are now defined with length as a meter is the distance light travels in a vacuum in 1/299,792,458 of a second. This is because the speed of light is defined as the 299,792,458 meters per second. Time is defined as the transition between hyperfine levels of the ground state of the cesium-133 atom. The amount of substance, 1 mole, is defined as 6.02214,076 times 10 to the 23rd constituents, that is, things, which is now a defined value. And the mass, the kilogram, used to be the mass of a certain cylinder that was kept in France, but now it is defined using Planck's constant, and the measurement can be made in other places other than comparison to the 1 kilogram mass that's kept in France. Here's a set of prefixes used in the metric system generally. At the top is 1 times 10 to the 15th power, which is a peta, symbol P, and we go all the way down to atto, which is a symbol of the lowercase a, which is 10 to the minus 18th power. And most of them are in units of threes, except for whenever we get to deci, centi. Those are not factors of 3. Deci is 10 to the minus 1, or 0.1, and centi is 10 to the minus 2, or 0.01. This slide for some reason came across incomplete, but the simplest way to perform a calculation is to change the prefix to its numerical equivalent. So for example, 1 centimeter becomes 1 times 10 to the second meters, replacing the centi portion, the C, with 1 times 10 to the minus second. We could also do that with 25.56 kilograms and convert that to grams and get 25.56 times 10 to the third grams, which when converted to scientific notation is 2.556 times 10 to the fourth grams. So, what is the distance across the nucleus of 1 femtometer in meters and in kilometers? The first one is we take the 1 femtometer and we replace femto with its equivalent, which is 1 times 10 to the negative 15th, and just put meters after that, and that is our conversion from femtometers to meters. To then convert to kilometers, 1 times 10 to the negative 15th meters is the femtometer, times 1 kilometer, and in the denominator for the kilo we put 10 to the third power meters. Thus the meters cancel and we get the units of kilometers, which is 1 times 10 to the negative 18th kilometers. Looking at another conversion, 53 attoseconds is the shortest known laser light pulse that has been created at the Florida Attoscience and Technology Lab at the University of Central Florida. As of 2017, how fast is this laser pulse in minutes? So we have to know the conversion factor. 53 attoseconds becomes 53 times 10 to the minus 18th seconds, and then we have to take the 53 times 10 to the minus 18th seconds and multiply that by 1 minute is 60 seconds, which cancel out the units of the seconds, which calculation gives 8.8 times 10 to the negative 19th minutes. We could have also done that keeping in the atto prefix and taken 53 attoseconds, took 1 minute divided by 60 seconds, and again the seconds cross out, but the atto prefix is kept, and we end up with 0.88 atto minutes, which is equivalent to 8.8 times 10 to the 19th minutes. In this slide, we're going to distinguish between mass and weight. Mass is the measure of the amount of matter in a particular object, measured in grams or kilograms or milligrams, but some subset of grams, with the kilogram being the SI unit. Weight, however, is the force that gravity exerts on an object, and it is a kilogram, which is our SI unit, multiplied by the force due to gravity, which is in meters per second squared, And that combined unit of a kilogram times a meter divided by second squared is called a Newton. This is one of our first derived units that has a special name. On Earth, because of our gravitational force, we find that 1 pound, which is the force exerted upon the object, is equivalent to 4.45 newtons. And this is the general conversion which will get us back and forth between a newton and the pound. Temperature is the measure of the average molecular motion of particles, or in essence, the average of the energy of all the particles in a system. Temperature can be measured in 3 basic ways. Fahrenheit, which is the English system, which is not commonly used in scientific measurements. Degrees Celsius, which is based upon the freezing point of water as 0 degrees Celsius and the boiling point of water as 100 degrees Celsius. This is the commonly used measurement. However, most measures of degrees Celsius are then converted to Kelvin, which is the absolute scale. The units of Kelvin and Celsius are equal in magnitude, that is 1 degree Kelvin and 1 degree Celsius are equivalent to each other. However, being the absolute scale, we subtract 273.15 from it to get degrees Celsius, or to get Kelvin from Celsius, we take degrees Celsius and add 273.15, with the bottom of the Kelvin scale as being 0. Here are several of the derived units. The liter, for example, is 1/1000th of a meter cubed, which is the SI base unit, the meter cubed. The Newton is the unit of force, which is a kilogram meter per second squared. The Pascal is the measurement of pressure, which is a kilogram divided by a meter per second squared. And the joule, which is our units of energy, which is a kilogram meter squared divided by second squared. There is a direct relationship between the units of volume in liters and the units of volume in meters cubed. And through the derivation of that, we find, in essence, that 1 milliliter is equivalent to 1 centimeter cubed, or 1 cc. And density is another derived unit that we usually measure in grams per milliliter or grams per centimeter cubed. Its formula is given by density equals mass divided by volume. Lower density substances like gases, density is generally given in grams per liter. This slide was supposed to have the density of platinum as 21.5 grams per centimeter cubed and a volume of 4.49 centimeters cubed. And the question is, what is its mass? Given that density equals mass divided by volume, we can convert this algebraically to mass equals density times volume. So the mass equals 21.5 grams per centimeter cubed times 4.49 centimeters cubed, which equals 96.5 grams. This slide was supposed to let us know the numbers from definitions or numbers of objects, that is, exact numbers, are considered to have an infinite number of significant figures. For example, if we take the average of 3 measurements, in this case 6.64, 6.68, and 6.70. The average is 6.64 plus 6.68 plus 6.70, all of that divided by 3. And since this is addition in the numerator, we are going to carry out the number of significant figures to 2 decimal places because each of these numbers goes out to 2 decimal places. We don't count the 3 as having significant figures, or we can count it as having an infinite number of significant figures, so that we end up with 6.67 as the answer to the average. When calculating the standard deviation or the average deviation, the value calculated will have the same number of decimal places as the calculated average. So for example, the 3 previous numbers, 6.64, 6.68, and 6.70, had an average of 6.67 measured out to 2 decimal places. The standard deviation is 0.03, not 0.0308. This is because there are only 2 decimal places in the average, and therefore we can only have 2 decimal places in the standard deviation. Accuracy and precision. Accuracy is how close the measurement is to the true value, and we generally measure that by the difference between the average and the true value, which we'll call the percent error. Precision is how closely the measurements are to each other and will be represented by the standard deviation or relative standard deviation. Things that are accurate are all tend to be clumped together and tend to be centered upon the true value, whereas things that are precise may not necessarily be accurate. They'll be clustered around each other, but will not be near the true value, as in the center target. Things that are not precise cannot also be accurate because the numbers are scattered everywhere. For each of sets of data below, we can describe the accuracy and the precision. Student A has an average of 0.333. With a true mass of 0.370, it is slightly off of the actual average. So the accuracy is not very good. The standard deviation, however, is 0.002, which is very low. So we can say that student A has low accuracy but high precision. Student B has an average of 0.357, which is closer to the true mass. However, the standard deviation is 0.019, which is much less precise. Data that is much less precise, even though it may be closer to the true average, cannot be considered accurate as well, even though it's not as precise. And student C has an average of 0.371 grams and a standard deviation of 0.002, making it both accurate and precise. And we can see that in the next slides as we look at the mathematical relationships of accuracy and precision. Accuracy is quantified by the percent error, which is basically the relative distance of the average from the true value measured as a percentage. So to calculate the percent error, we take the average measured value and subtract the true value, then take that and divide it by the true value and multiply the final answer by 100%. As we saw in the previous set of data, the error for A was going to be fairly large because 0.333 is a fair distance from 0.370, and the percent error is minus 10%. The percent error in B is minus 3.5%, but again, as we said, it looks like it's more accurate. However, the precision wasn't as good. And the percent error in C is 0.27%, which is an expected value because the value was so close to the true value. Again, I have another slide that's been misinterpreted when translating it. But here, precision, we're going to quantify by what's called the relative standard deviation, or RSD. To calculate it, you take the standard deviation and divide by the average, then multiply by 100%. And if we were to calculate the relative standard deviations for the previous three sets of data, we would find that student A and student C had a very low relative standard deviation, and student B would have a higher relative standard deviation because its standard deviation was much larger than the standard deviations of the other two. Some notes on problem solving. First of all, read carefully. Find the information that's given and what is asked or desired of the problem. Find the appropriate equations, constants, and or conversion factors that you need. Next, after doing the calculation, check for the sign. That is, if you expect a positive sign and you get a negative one, something went wrong in your calculation. Check the units. That is, if you're expecting pounds, then you should not be getting feet for your units. And also check significant figures. And finally, check for reasonability of the answer. You may not have enough experience right now to know if an answer is reasonable or not, but if you start out with a large number and do a calculation, you might reasonably expect large numbers at the end of the calculation. However, chemistry is definitely full of tricks, and the reasonability of the answer I will explain for each different type of problem to help you out. Well, let's look at problem solving here. The speed of helium at room temperature is approximately 1,250 meters per second. Let's convert that to miles per hour. So we'll take 1,250 meters per second, and we need a conversion factor to go from meters to miles, and we have here 1.609 kilometers per mile, or 1,609 meters per mile. So that will convert meters to miles. Next, we need to convert seconds to hours. So we have 60 seconds per minute and 60 minutes per hour. And when you calculate all of this, you get 2,797 miles per hour. But we need to look at the number of significant figures. This original piece of data has 3 significant figures, the 1, the 2, and the 5. The 0 does not count. In the conversion factors, The 1.609 has 4 significant figures. 60 seconds per minute is an exact conversion because it's a definition. 60 minutes per hour, again, is a definition, so it's an exact conversion, so we don't worry about significant figures for those. So our answer needs to have 3 significant figures. In order to do that, we're going to have to round this up, but we can't write it as 2,800 miles per hour because that shows only 2 significant figures. So we're going to have to give this as 2.80 times 10 to the third miles per hour in scientific notation in order to get 3 significant figures. Acceleration due to gravity is 9.80665 kilograms per second squared. What is that value in pounds per minute squared? Well, first of all, let's look at the conversion from kilograms to pounds. So 9.80665 kilograms per second squared. And our conversion factor is 1 pound is 453.6 grams. But we need those grams to be in kilograms. So the conversion factor is there are 1,000 grams in a kilogram. Next, we have to get rid of the second squared and put it into minutes squared. There are 60 seconds per minute, but because the seconds are squared and we want minutes squared, this value here at the end has to be squared. Now we'll get rid of kilograms and seconds squared and leave us with pounds per minute squared, and that value is 77831 pounds per minute squared. What are the correct number of significant figures? In this case, the original data has 6 significant figures, but the conversion of pounds to grams only has 4 significant figures. And remember that the 60 seconds per minute is a definition, therefore we don't count significant figures there. So the answer is going to have 4 significant figures. 77830 pounds per minute squared. Finally, let's look at a little bit more complex of a problem. We want to convert 21.5 grams per centimeter cubed, which is the density of platinum, and convert that to the density in pounds per inches cubed. So 21.5 grams per centimeter cubed. To get rid of the grams, we use the 1 pound is 453.6 grams. That takes care of the grams. And to get to inches cubed, we have 1 inch is 2.54 centimeters. But this whole conversion factor has to be cubed to get rid of centimeters cubed. So the answer comes out to be 6.57 pounds per inches cubed.